we shall discuss in this module regarding the factors which are responsible during the course of motion of projectile or projectiles in the bore of the weapon. We have already discussed many factors in part 1 of the module, but there are several others which need to be attended to, and they are creation of the high pressure in the barrel, calculation of the muzzle velocity of the projectile, and third is bullet jump and vibration. These factors will be discussed in this module. So far as the pressure is concerned, the barrel is declared safe only when it is tested by the manufacturer. When it is tested for 40% more of the pressure it can withstand, then it is intended to stand. Thus, in case of a rifle which generates a pressure of 50,000 pounds per square inch, the testing will be carried out for 70,000 to declare it safe for its use. The pressure developed depends upon many factors, including the quality and quantity of the powder, the space available for the expansion of gases in the barrel, as well as the movement of the projectiles. So far as bullet jump and vibrations are concerned, it may be stated as soon as the projectile start moving forward, the weapon starts going up in position as well as going back according to Newton's law of motion. The jerk created depends upon a number of factors. The most important of one is how the weapon is held by the shooter. So far as the calculation of velocity and generation of pressure is concerned, they have been discussed very well in this schedule. So far as bullet jump is concerned, it is quite noticeable in case of handguns, say revolvers and pistols, but it may not be so in case of rifles, because the double barrel guns and rifles may have vibration sideways also. It depends upon the manner in which it is held against the body. The number or the quality or the quantity of jump will depend upon the manner in which it is held against the body of the shooter.
After studying this module, you shall be able to know factors concerning internal ballistics. Learn how to calculate the barrel pressure. Know how to calculate the velocity of bullet. Know what is bullet jump. Internal ballistics is the study which deals with the motion of a projectiles in the bore of the weapon, and involves a large number of factors. Some of the factors, namely lock time, ignition time, barrel time, density of loading, burning of powder, problem of heat generation, influence of atmospheric parameter, etc., have been discussed in the part 1. The following additional factors concerning internal ballistics are discussed in this part 2, and the remaining factors would be discussed in part 3 of internal ballistics. Creation of barrel pressure and its measurement, velocity of bullet and its calculation, bullet jump and vibration. Barrel pressure and dimensions. Two of the essential parts of a weapon are barrel and action. Manufacturing processes, specifications, and tests are conducted to assess the limit of barrel life and non-failure of action. Before any barrel is accepted for use, it is proof-fired with a high-load test cartridge which is capable of producing at least 40% more pressure in the barrel than the lead which is intended to withstand. To have an idea of the magnitude of pressure developed in barrel, an example is cited. A service rifle is expected to withstand a barrel pressure of 50,000 pounds per square inch, but test fires would be conducted with ammunition giving rise to a pressure of 70 or more thousand pounds per square inch. The objectives of such post-manufacture tests are to find any fault in design features and to correct them and establish its suitability for a safe use. While in non-standard weapon or country-made firearms, failure of barrels takes place quite frequent. Tremendous pressure is developed in the barrel of a firearm during the firing process. There are several factors responsible for it. Some of the important factors are detailed: the quality and quantity of powder charge, the available space for expansion of gases produced, the chemical nature of the powder, surface area of the burning propellants. Different types of powders, namely progressive powders, degressive powders, and constant burning powders, produce different maximum pressures. Maximum pressure developed is considerably less in the case of progressive powders than in other powders. The pressure developed by the various types of powders inside the barrel. Vertical line represent pressure. This curved lines relates to the degressive powders, where the burning surface area decreases continuously. The second curve relates to constant volume burning surface area powders. Curve relates to progressive powders. The maximum pressure is considerably less than on other powders. Pressure. Formation of excessive pressures may bust the firearm, causing at times even fatal accidents. Such cases come up in criminal investigation. Likewise, the development of low pressures in some firearms used in commission of crime may lead to unexpected types of injuries which require careful evaluation. Hence, it becomes essential to measure and understand the formation of pressures inside the barrels. There are additional factors which contribute to the development of pressure to some extent, namely shape of the cartridge case and depth of grooves in the barrel. For the same quantity of powder, greater pressure will be developed if there is an abrupt junction between the neck and the case. Measurement of pressure. The pressure developed by ammunition is always measured to find out if the firearm is within the safe limit or not. Ordinarily, the measurement is done in the factory itself. There are different methods for determining the pressure. Methods of measuring barrel pressure. Assuming that the weapon is in a good condition and that the correct type of ammunition is being used, it is the pressure produced in the barrel which ultimately decides whether the bullet will reach the muzzle, exit from the barrel at an acceptable velocity, or destroy the weapon completely. Often, weapons are received with reloaded or homemade ammunition and for safety's sake, it is often necessary to determine whether the ammunition is in fact safe to fire. At other times, it is necessary to evaluate the suitability of an ammunition weapon configuration and once again knowing the barrel pressure produced could be advantageous. Knowledge of basic facts concerning how the pressure is measured and what the figure means is therefore a useful adjunct in this field. The measurement of maximum chamber pressure is carried out with a pressure gun. This is a very strongly built action and barrel with a hole drilled into the top of the chamber. Clamped over this hole is a closed tube with a free moving piston. Between these piston and the closed end of the tube is inserted a small disc of metal of a known and uniform hardness. On firing the cartridge, the pressure produces forces the piston up against the metal disc, which is crushed against the closed end of the tube. Crushing the metal disc in this way reduces its thickness by a measurable amount. By subjecting similar discs to known pressures, it is possible to calculate the pressure of any cartridge by measuring the compressions of the disc. As no single metal will give consistent result over wide range of pressures, discs made of lead and copper are used. The lead discs are for lower pressures. As the discs only give accurate pressure figures over the mid part of the range, they cannot be accurately related to actual pressures in pounds per square inch or in kilograms per square centimeter. As a result of this, the results are referred to as lead or copper units of pressure. In modern pressure guns, the metal disc is replaced by a small quartz crystal. This crystal will, when subjected to pressure, produces a tiny quantity of electricity which can be directly related with greater accuracy to the pressure exerted upon it. These are called piezoelectric pressure guns. The pressure measured with these guns is referred to in pounds per square inch or in kilograms per square centimeter. High pressures are a necessary evil for the simple reason that the greater pressure, greater will be the velocity of the projectile being pushed by the expanding gases. This is true in cases of both quick burning powders and non-progressive powders, but high pressures result in some unwanted effects described below. Increased recoil of the weapon, increased wear and tear of firearm, increased temperature in the barrel. Velocity of bullet. The designer of firearms and ammunition have aimed to hurl projectiles with a suitable velocity so that they strike targets at a particular range, keeping in mind to strike a balance between charge weight and velocity of recoil of the firearm. Since every action has an equal and opposite action according to Newton's law of motion. The muzzle velocity depends on several factors, namely quality and quantity of powder, barrel length, bullet fit, mass of the bullet, and its shape as well as bore of the weapon, etc. For putting any projectile in motion with the velocity v, energy is required which is equal to half mv square, where m is the mass of the projectile. If a stone is thrown manually or through other means, energy required could be supplied by the person throwing the same because it is small. In case of small arms, the velocity generated is much higher, so chemical energy is harnessed for the propelling of projectiles. Calculation of muzzle velocity. According to Newton's law of motion, velocity is equal to force in pounds divided by the mass. Mass is weight of the object divided by the acceleration acting upon it due to gravity, that is 32.14 feet per second. This is given by V is equal to Ft by m, where V is the velocity, t is the time during which force acts, and m is mass of the object. Also, if the force is allowed to act through a distance rather than a given length of time, then V is equal to under root 2fs by m, or V square is equal to 2fs by m, where s is length of the barrel, f is force in pounds, m is mass of the missile, and v is the velocity. Example: let us consider an example of a firearm having bore diameter of 0.45 inches with a chamber pressure of 1400 lbs. Pressure is force per unit area, and in this case diameter is only 0.45 inches. The force applied would be F is equal to 14,000 into 22 by 7 into 45 by 2 whole square is equal to 2225 lb approximately. Thus, if a force of 2225 lbs would be acting on the base of a 0.45 inches bullet which weighs 230 grams along with a barrel of 5-inch in length. Converting 5-inch to 5 by 12 feet and 230 gram to 230 by 7000 lbs, we have V is equal to under root 2 into 2225 into 5 by 15 into 7000 by 230, which is equal to under root 1815390, which is equal to 1347 feet per second. The velocity calculated by using the above formula comes out to be 1347 feet per second and is very much different from the published figure by the manufacturer, which is 810 feet per second. Bullet jump and vibration. As soon as the projectiles starts the forward motion, the firearm starts moving backward and upward. Movement of the barrel is called jump. The jump is noticeable in handguns. A double-barreled gun suffers sideway vibrations. The vibration and the jump are considerably affected by the manner in which the firearm is held. These vibrations are comparatively smaller when compared with those caused by the movement of projectiles in the barrel. Some vibrations are caused as soon as the release and striking of hammer takes place. Rotation of gun takes place in an upward direction. As mentioned earlier, the force which acts on the rear of the bullet to propel it forward is also exerted on the base of the cartridge case to move it backward. The formula for this, as mentioned before, is V is equal to Ft by m. It is this force which causes the weapon to recoil, which will be discussed in great details in the third part of internal ballistics. This force not only drives the gun to the rear, but because of the barrel is situated above the hand and therefore above the rotational axis of the wrist, it also rotates the gun in an upward direction. As the bullet is traveling down the bore during the period in which the barrel is lifting, it will strike the target above the point at which the barrel was pointed when the trigger was pulled. The actual time the bullet remains in the barrel is extremely short, of the order of 0.001 seconds, but it does change the situation as the muzzle lifts the point of aim by a fraction of an inch. This does, however, has a pronounced effect in the striking point of bullet and change the impact point by more than 1 inch at 100 yards. In most of the standard weapons, flight is regulated for a set of certain weight bullet traveling at a certain velocity. The situation in case of non-standard weapons or country-made improvised weapons is quite different, since no such setting has been seen and thus efficiency remains quite low. It is quite interesting to note that the heavier bullets strike above the point of aim and the lighter one below. This is exactly opposite to common sense would indicate. Here is an example of barrel lift. When a standard military P14.303 inches rifle is fired with standard military ammunition, weapon recoil will cause barrel to rise by zero point 0.1 inch between the time trigger is pulled and the bullet leaves the barrel. Summary. Some of the factors concerning internal ballistics are creation of barrel pressure and its measurement, velocity of bullet and its calculation, bullet jump and vibration. Maximum pressure developed is considerably less in progressive powders than in other powders. According to Newton's law of motion, velocity is equal to force in pounds divided by the mass. This is given by V is equal to Ft by m. The muzzle velocity depends on several factors, namely quality and quantity of powder barrel length, bullet fit, mass of the bullet and its shape, as well as bore of the weapon, etc. The measurement of maximum chamber pressure is carried out with the help of a pressure gun. As the projectile starts forward motion, the firearm starts moving backward and upward. Movement of the barrel is called jump.